Hmm. Bro, my stream just like randomly broke and I don't know why. And it like I was trying to stream and it just literally just kept crashing and crashing and crashing. Out of nowhere too. Like out of absolutely nowhere. That's annoying. That's super annoying. Well, we're back. After being broken for a little bit, I still did not go to the bathroom because I was trying to fix this. So here we are. When we get back, and well, I want to take like a quick 10 minutes. Probably could have just stayed off stream and came back on, but I'm gonna take a quick 10 minutes. And then we can get into this. I do want to double check to see if I can stream Zybucks. So yeah, we're gonna do that when we get back. But for now, enjoy the screen. Okay, I'm back. Cannot stream Vibooks. Looked it up. It's in their terms of service. It is not allowed. I repeat, it is not allowed. So for anyone that wanted to do it like I did, and you're watching this in the future, just know you can't stream it. How's that looking on sound? Looking good enough. Looking good enough. Okay, so what am I doing here? Okay, this guy's a ban. I'm not banning people, bro. Oh shit! Actually, oops. I mean to cuss. Actually, how do you ban people? I don't know how to ban people. Okay, so I reported them. Okay, now how do I ban them? I do not know how to use this. Click their name. Okay. And timeout user? No. Warn, timeout. Oh, ban. There it is. It's right there. Hello. Completely missed that one. Okay. Give me a second. Sorry. Oh, is that my email? Oops. I did not realize my email was just out in the open like that. Oh, that's not good. That's not good at all. Was there anything on there important? No, I mean, you guys already know my name. No, there's nothing too serious on there. No, nothing too serious. Dang. That was a gaffe, to say the least. I'm not a fan of this song. Whatever it is. Where is my music? There we go. Interesting. Okay, let's get back into the math. Uh-oh. What did I do here? Why is my iPad not showing up? Oh no, that's not good. Did it die? Oh, it's like going in and out. That's not good. I swear I was at 29% just a second. I was only at 30. Let's see if we can do something about this here. Give me a sec. I'm trying to get my iPad back on the screen here. Decided to just not do what it's supposed to do, so need to figure out a solution. All right. Oh my gosh. I finally got it to work. I don't know what happened. Like everything just stopped working for some reason. It really just all broke at once, dude. That's so annoying. Okay, there we go. Everything's back to normal. I think my mic looks like it's coming in fine. Face looks like it's coming in fine. Yeah, it literally just stopped. Like I came back to my computer and nothing worked. Don't know why, don't know how. But that is what happened, so I had to troubleshoot a little bit. We're all good. We're doing great. Everyone's having a good time. Everyone's living life. Everyone's enjoying themselves, I hope. Microphone is probably a little quiet. That's okay. Might just have to put it down here and hope for the best. And that's all we can really ask for. Okay. Yeah, so let's just get straight into the video. I think I want to watch the videos and then do the practice questions here on OpenStax, right? Because what is this going over? Let's see. Does this have... So find the area of a curve, the tangent problem, area problem. Okay, so this seems like... This seems pretty... Yeah. This seems like more or less 1, 2, 3, 4. 4 chapters. This seems to me more or less to be the same exact thing. Yeah, I changed my username just to be more consistent throughout all of my social media accounts. And because that old username was linked to too much stuff that had my real name, so I had to switch that up. Yeah, I'm doing good. Gotta crank this math out here. Been slacking for about a month. I need to have this done within the next 3 weeks, so hope you're doing good too, though, Octaris. It'll be pretty boring for the next like 2 weeks while I just crank this out here. Uh-oh. All right, let's see here. So we can stop this music that's playing. All right, let's get to this video. Introduction to limits. Oh yeah, here we go. Oh yay. I don't know how to do limits, sir, Mr. Sir, but I hope that you can teach me. Let's see here. I need to create a new notebook, and let's name it limits, if it will let me. There you go. Oh yeah. I like the dark paper. Sometimes I don't like black paper. Yellow is pretty ugly though. I think black just contrasts better on oh, you can have any color? That's pretty wild. That's disgusting actually. I think the black just contrasts better on the screen though, so let's just go with black. All right. What do we got here? I'm kind of hungry. No, I'm not ready at all, but let's do it anyway. Oh, that looks like it's too quiet, so let's turn that up. Maybe we're right there.
Goal number 1. The first goal, the one that we're going to spend most of our class on, at least the first half of our class on, is this goal. Given any curve, not straight lines are easy, but given a curve, I want to be able to find the slope of a curve at a point. Isn't that an interesting idea? If I say to you, I want you to go ahead and find me the slope at that point. Right now, we really have no idea how to do it. I mean, you can approximate it. You can go, oh, okay, I'll find the slope. Let's see, slope is 1/2. Is that accurate? No idea. Right? Well, we can't really just kind of approximate slope. What we're going to do is find out a really good way using calculus on how to find the slope of a curve at a point.
I just don't understand why I need to find the slope of a curve at a point. Is there ever a time where knowing the slope at a curve at one particular point will ever make my life any easier? Like, for example, if I'm like what do you call it? If I'm looking at like CDC or something, there's like this weird slope of like, it's kind of exponential, but then it kind of turns into a log. Like, do I really care about what the slope was at this one point? Actually, you know what? Maybe I would. Like, if I want to know what the rate of... Wait, let me think this through really quickly. So if I look at like COVID cases, and over time it's changing, there's, time on the x-axis and the amount on the y-axis, amount of cases. And I want to see at 5/10/2023, how many cases were there? Why would this... Slope is the rate of change. So why, I guess, how do you even know the rate of change at one point? I guess that's what he's going to describe. But I don't know why I would need to know the rate of change at one particular point instead of the rate of change over time. Which is just a function. But maybe eventually you can find the function of a curve. Because I don't know how the hell you would do that. I have no clue, bro.
In fact, when I ask you a certain thing in this class, you're going to say, oh, it's the slope of a curve at a point. We're going to talk about that for a long time. That's goal number one. Goal number one is to find the slope of a tangent, or to find the tangent to a curve at a point. The tangent is the line that intersects a curve at one spot in an area. So goal number one. Find the tangent which involves the slope of the curve at a point. That's goal one. If we can do that, we're on calculus fast pace. That's good. So
nice.
Find the slope of that curve at a point. That's going to lead to the tangent and vice versa. Tangent and slope go hand in hand for us. Goal number two, which is the last half of our class, maybe a little less than that. Goal number two it's also a really interesting question. So cool. By the way, this stuff is stuff you can't answer in any other class, right? You can't do that with algebra. There's no way you can do that with algebra. You can't find the slope of a curve. Are you kidding me? Slope of a straight line, easy. Slope of a curve, wow. Is that not an intriguing idea to you? It should be. If you're in this class, you're like, oh, that's kind of cool. How can you find
I don't find it intriguing.
The next question is probably even a little bit more interesting. The next question is, let's suppose I have some funky, any curve that you can think of.
Okay.
Can you, between 2 points, find the area under that curve? Can you do it?
Why do I care?
The answer is right now, with what you know, can you do that with geometry? Because I can say, okay, great, find the area of something that's curving. Can you do that? No, you can't use the area for rectangle, that's not rectangle. You can't use the area for triangle, that's not triangle. You can't break this up in any way that you have geometric figures, can you? Not even circles, not even with radiuses, because the radius is changing. So the next question is, can you find the area under a curve? Those are the two goals of calculus. Find the slope of a curve at a point, and secondly, can you find the area under a curve between 2 points?
I just don't. I need to. Okay. I can't. I suck at doing things I don't want to do. I need to find a valid reason to do the things that people say I should do. I don't know if that makes sense to anyone else, but like, I'm being told I have to do calculus just because I have to pass the class. But in my head, that's not enough. That's not good. I don't find that appealing. I need more. So let's see if someone can convince me. Because I can't convince myself why I should like calculus. Because maybe there's some secret answer that calculus is like one of the greatest things to ever exist in the world. And I just don't know it. Maybe I'm wasting time by watching these videos instead of, paying attention. All right. Two videos.
Despite what you might have thought, math is not just meaningless formulas that popped out of nowhere. Even though you might not be able to see it, it's everywhere in our universe. Among the realm of mathematics, there's one particular field described by the Nobel-winning physicist Richard Feynman as the language of God, calculus. Scary, huh? Well, it's basically just a description of changes in our ever-changing universe. Normally, when we talk about changes in stuff, we talk about the difference in the amount of stuff after the change. Well,
Yes.
we can also talk about how fast something changes, the rate of change, how much something changes in a period of time. To find the rate of change of the height of this bean sprout, we found out how much it has grown within a period of time. Dividing the height by the time gives you the rate of change, 1250 meters per second.
Okay.
Easy, right? But if you're a good observer, you'll probably notice that most things don't change at a constant rate. So the method I just mentioned doesn't really indicate the variations in the rate of change throughout the entire motion. Perhaps we can chop the motion up according to its speed, like fast period and slow period. Yeah, but it's perhaps still not precise enough. How about dividing it into smaller chunks, like tracking the change in the distance every second, millisecond, nanosecond, or even 0 seconds? Wait, what? Nothing can change within 0 seconds when time doesn't even pass. Well, even a powerful subject like math can't change something absurd into something sensible. What we can do is to record the change within an infinitely small period of time. Almost 0 seconds, but not exactly 0. We call this small period of time delta x. As delta x decreases, you see the rate of change approaching a certain value. And from there, we can approximate the rate of change at a specific moment. This process is called differentiation. What's so amazing about calculus is that not only we can use it to find out the instantaneous rate of change, but also to do the reverse. Given how quickly something changes, we can know how much something has changed. To find out the distance traveled from the speed, we can multiply its speed and the change in time. But what if the speed is not constant?
What?
We can chop its motion up into very small periods delta x, and then add all the distances traveled within each small period up to get the total change in the distance throughout the entire motion. As delta x decreases, approaching 0, you can see the total change in distance approaching a certain value. This process is called integration. You might ask, why do we care about calculus apart from nailing exams? Well, many people do care. Scientists use it to describe the changes in our natural world, engineers use it to optimize their designs, and economists use it to optimize profit.
Dude, my iPad is broken. My iPad is like actually completely broken. It's saying that my battery's at 100%. It's saying that it's 941. It's like I'm looking through a snapshot of what my iPad was at one point, and it only does it when it's plugged in. That's so odd. So odd. When it's not plugged in, it doesn't do it, but when it is plugged in, it just breaks.
Even if there isn't any point in your life that you have to apply calculus to real-life problems, well, isn't...
Hey everyone, how's it going? One of the first videos I made on this channel was about why people reasons I think why people fail. There is a miscommunication between what the teacher expects and what you expect. So what do I mean by that? I've seen it over and over again. The student comes to me with a test which they did not do very well in, and they say to me, I thought I studied and I thought I knew it, but when it came to test time...
Okay. Let's just do it. Stop all the yapping. And let's just get straight to this money. Let's go. Let's go.
And amazingly, it's actually not that hard. I think it's easier than pre-calculus. It's easier than that. You don't have to do, maybe not easier, but if you know pre-calculus, it's not such a big going to talk about first, we're going to talk about the tangent problem. I'll give you a very intro to this, but I'll talk about it later on. We're going to talk about this for most of our day-to-day. So let's talk about the tangent problem. Are you ready? Do you have any questions on the ideas of the goals of calculus? Do you understand what the goals are? The goals are A, find the tangent or the slope of a curve at a point. That's what we want to do. Goal number 2, after we finish this, we're going to move on to find the area under a curve between 2 points. Very cool ideas. So let's work on the tangent problem right off the bat.
The tangent problem. Okay, all right.
Okay, this is it. This is like the fundamental idea of calculus.
We're getting straight into it. We're cutting straight to the chase. We are going straight to the source. I don't like that skinniness. I like it thicker.
Calculus is so cool. We're going to figure out what a limit is from doing this idea right here too. Here's the tangent problem. The tangent problem says, if you give me any arbitrary curve, so I'm just making it, I don't even know what that is, it's just an arbitrary curve, and you give me a point, let's call that P. Give me a point, call it P. I want to be able to find the slope of that curve at point P. Do you get the idea? Talk about the tangent problem right now, right? Slope of that curve at that point. Because if we have the slope and we have the point, we can make the equation of the tangent. Do you get me? That's pretty easy. That's just y minus y1 equals mx minus x1. So right now we have the point. What we're worried about is the slope of the curve at that point. Do you follow? Now the problem is this. If we're going to make a tangent line, how many points do you need to make up a line? How many points?
Infinite points.
That's the problem. Right? How are you supposed to make the equation of a line when you only have 1 point and you don't know the slope yet? Do you see the issue? That's the problem.
Yeah.
So here's what we're going to do. We're going to say, okay, well, let's put some point somewhere else on this thing. How about Q? Up there. If I connect these two things, those two things, do you remember what it's called when you connect 2 points together? It's not a tangent, it's a, do you know? It's a secant. That's some geometry. Secant connects 2 parts of it, well, usually a circle, but of any function. So
I do not remember that from geometry.
PQ is a secant line. It touches 2 points of this curve.
Oh, I should be writing this down, boys. I'm dropping the ball here. I did not write any of this down. I didn't think it was that important, but apparently it is. A line, some arbitrary slope. We have slope P and the point Q. And so we draw a line between both P and Q. We can then say the line PQ is a secant line.
Now here's the question, all right? You agree that we need 2 points for a line, yes? But we also agree that we want the tangent of point P. That's the ultimate goal here. So my question to you is PQ a good approximation for the tangent? Is this a good approximation for this?
No.
It's an approximation, right? They're both positive, okay, sure. What I'm asking you is there a way, think about this for a second, is there a way that I can make this secant approximation better to make it more approximate the tangent? Can I make this a better approximation? How could I do it? Let's assume for a second that P is fixed, but Q is movable. You can move the point Q. I can't move P, but I can move the point Q. Can you move Q to make this secant line a better approximation to our tangent line? Can you think of that?
I'd probably move it closer to P.
Would you move it up? Would you move it down? Let's see what happens. It's going to be interesting. So we're going to find out what happens as we move Q down this line. So if I move Q here, is that better or worse?
Better.
Better, because I'm going to have, let's use different colors here. That. This would be like Q sub 1, maybe a different point for Q. If I move it closer, is it going to get better or worse? Better. Okay. If I move it closer, it's going to get even better. If I move it closer, it's going to get even better. If I move it closer, it's going to get even better. When do you stop? Can you move it really, really close?
Yes.
Can you move it so Q and P are the same point? Why not?
No. Because there's no change.
So can you move it close? The answer is, sure, we're doing it right now. Can you move it close? Yes. Can you move it so close that there's no difference between them? Yeah. Can you make it the same point? No. That would fail because we need 2 points. I don't care how close they are, but you need 2 different points, right? If you have 2 different points, you can make the equation of a line. That's great. That'd be fantastic. That's our idea, actually. So we're going to try to move the point Q really, 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 really close to the point P. If we can move it really, 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 really close, that's math speak, by the way. Really, 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 really. That means very, 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 very. If we can move it really, really, really close, then our secant line is going to be really, 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 really close to a tangent line. Do you agree with the idea? So you take this point, you go, let's move it really close. Not really far away, that's a sucky approximation. But if you move it really close, move that secant really close, that point really close, that secant is so close to a tangent line that it's not going to make a difference. That's the idea. So let me write some of this stuff out for you. So what we're doing right here, we need 2 points for a line, sure. We understand that. Awesome. So we have the points P and Q. Well, the question we're asking is, what happens as Q gets closer to P? And the answer is, as Q gets closer to P, we just talked about this, we just said this, and there's nothing new. As Q gets closer to P, the secant line more closely approximates the tangent line. Not sure if you understood that at the first, okay. So as
Bro, what?
Q approaches, I'm gonna use that word, we're gonna use that word limits as well. Approaches, that means gets closer to. As Q approaches P, we get closer to a tangent, or in other words, the secant more closely approximates the tangent. Okay, well that's great, that's great. Oh, one more little note. Why was it that we can't just let Q equal P? What was the reason? Why can't we just say, oh, let's move to P? Okay, there wouldn't be 2 actual points at the same point twice, and that's the problem. We couldn't make an equation of a line with that. So one little note, we can't just let Q equal P because we need 2 points to make a line. You need 2 points. That would be a problem. Here's the idea of a limit, all right? This is a big idea. Here's the big idea for limits, okay?
Okay, big picture, big picture.
The idea is, how close can you get one point to another without them being the same point? So let's say I have 2 points like this. Can you find some space between it? Let's say move it over to the midpoint. Can you find some space between it?
Isn't the answer infinitely?
Space between it. Can you keep doing that for eternity? Between any 2 points, there's a gap. In that gap, you can fill it in with another point. Because points have no breadth. That means that even though we draw them on the board like this, they really don't have any distance between them. So 2 points can get, would you agree, infinitesimally close to each other. That means so close that you can't put anything between them, but there's still some little distance. And then you can get even closer to that, and closer to that, and closer to that. Would you agree to that? So here's the idea behind calculus. It says we can get Q so close to P that there's literally no difference between the secant and the tangent. We can get it so close, we can't let it equal, but we get it so close that the secant line is the same as the tangent line. That's the idea of a limit. Isn't that kind of an interesting idea? Yes, they're different points, but they're so close, it doesn't matter. That's the whole idea. So the big picture for our limits is, if we let Q get really close to P, the secant will be identical to a tangent. That's the idea. Or approximate it so close that it doesn't matter.
I mean, didn't he already say that? As Q approaches P, the secant more closely approximates the tangent? Is that kind of the same idea?
If we let Q get really close to P, I'll use a better word, I'll use a more mathy word for that in just a minute. Really close to P, the secant will be identical to the tangent.
And I guess this is what the whole idea of a limit is, huh? As Q approaches P infinitely, the line looks indifferent to a tangent.
Here's the idea, right? Here's the idea. Now I'm going to replace this really with a key phrase for you. The idea of really, the idea of moving P or Q really close to P is called a limit. Moving something really close without actually getting there. That's the idea of a limit. You kind of understand the idea of a limit?
Oh, a limit. Okay.
We would say that Q would be in a limiting position. That means we've got it all the way really as close as we can to P, but it never touches P. That's the idea of a limit. It gets really close. So the idea of really close is a limit. In the most simple terms. So this is it. Would you like to see an example of how to actually do this? Would that be interesting to you? How to find the slope of the curve at a point? You want to see that? It's kind of fun. Okay, we're going to work through this. I'm simply doing this to give you an understanding of how limits work and the jump that you can make, okay? We're not going to be doing a whole lot of math like this. I'm just giving you an introduction right now so that you see it's possible with some real math stuff that you've had before without actually teaching you limits and calculus. I'm going to make one limit jump in this problem. I'll show you what it is, but this is stuff that you could actually do. We're just going to use calculus to do it better. You ready for it? Do it more mathematically.
Okay, all right. Let's do it.
Before I go any further, did you guys understand the tangent problem? Not sure if you're okay with the tangent problem.
Yes.
Limit. Moving a point really close to, but never actually getting there. Again,
Wait.
why can't we get there?
I do want to read the tangent problem. As much as I understood it, he gave a nice little overview, but I like to dig in the weeds a little bit. So let's see if we could find this tangent problem here. Okay. The tangent problem in differential calculus. Let's get some music going just so that you guys aren't being bored by my voice. I understand. This is boring. This is boring as heck. You know? Who truly wants to, like, if you wanted to watch this, you could just watch Dr. Leonard by yourself. Genuinely. So I got to give you a reason to want to watch me. Which is that I'm funny as heck, obviously. Obviously. One of the funniest people on earth. I'm just kidding. What does hubris mean? Was I being hubristic? Was I being... Whatever. I don't care. I don't have the time to look it up. Let's just get straight into it. Rate of change is one of the most critical concepts in calculus. We begin our investigation of rates of change by looking at the graphs of three lines. F of x equals negative 2x minus 3, g of x equals 1/2 x plus 1, and h of x equals 2. And here we have all of them. Why is it not getting larger? I can't see anything. There we go. I have terrible eyesight, by the way, guys. Terrible eyesight. And it doesn't help that I'm using, I am using, what am I using actually? What am I using? Oh, I'm wearing contacts. These contacts for some reason just aren't great. Okay. So this is negative 2x minus 3. This is x. The 1/2 x is the same as x over 2 plus 1. And then this is h of x equals 2, which is just a straight horizontal line. Okay. Easy enough. As we move from left to right, along the graph of f of x equals negative 2x minus 3, we see that the graph decreases at a constant rate. For every 1 unit we move to the right along the x-axis, the y-coordinate decreases by 2 units. This rate of change is determined by the slope, negative 2, which we see here, of the line. Similarly, the slope of 1/2 in the function g of x tells us that for every change in x of 1 unit, there's a corresponding change in y of 1/2 a unit. The function h of x equals 2 has a slope of 0, indicating that the values of the function remain constant. We see that the slope of each linear function indicates the rate of change of the function. Nice. Okay, compare the graphs of these three functions with the graph of k of x equals x squared, which is down here, simple parabola. The graph of k of x equals x squared starts from the left by decreasing rapidly, then begins to decrease more slowly and level off, and then finally begins to increase, slowly at first, followed by an increasing rate of increase. That's a crazy sentence. Followed by an increasing rate of increase as it moves towards the right. Unlike a linear function, no single number represents the rate of change for this function. We quite naturally ask, how do we measure the rate of change of a nonlinear function? That's a good question, sir. That's an excellent question. How do we do it? How do we do it? We can approximate the rate of change of a function, f of x, at a point a, f of a, on its graph by taking another point, x, f of x, on the graph of f of x. Why do they have to be so confusing when they speak like this? Huh? Why do they have to be so dang confusing? I don't get it. It's so crazy. Give me 1 second, guys. Okay, there we go. I had to add some tags to the thing to help with visibility a little bit. Okay. So we were talking about how confusing this was. Drawing a line through 2 points and calculating the slope of the resulting line. Such a line is called a secant line. Woo! simple secant line, a line through 2 points. This figure right here shows a secant line to a function f of x at a point a f of a. Beautiful. And the slope of secant line equals f of x minus f of a, f of x minus f of a, divided by x minus a. Now, my algebra folks know this is y2 minus y1 over x2 minus x1. They're using more sophisticated terminology, so not as simple, I guess. But this is the secant line. Finding the rate of change of 2 points is the secant line. But the problem is the accuracy of approximating the rate of change of the function with a secant line depends on how close x is to a. As we see in figure 2.5, if x is closer to a, the slope of the secant line is a better measure of the rate of change of f of x at a. As we see here, that was the first one. Now we got a different one, right? And this one is a lot closer than the first one. The secant lines themselves approach a line that is called the tangent to the function f of x at a. The slope of the tangent line to the graph at a measures the rate of change of the function at a. That was a really confusing sentence, but let's keep going. This value also represents the derivative of the function f of x at a, or the rate of change of the function at a. This derivative is noted by f apostrophe a, which is the derivative of a. Differential calculus is the field of calculus concerned with the study of derivatives and their applications. Oh, they got a website. We'll go to that afterwards. This illustrates how to find the slopes of secant lines. These slopes estimate the slope of the tangent line, or equivalent, the rate of change the function at the point at which the slopes are calculated. We continue our investigation by exploring a related question, keeping in mind that velocity may be thought of as, okay, you know what, this is actually so much more confusing than what he explained. So I like the way he explained. What is all this? This is crazy. What am I looking at? Can I drag it? Oh, whoa. So my understanding is that why is this a triangle? Why is this a triangle? What is this? This is the change in, oh wow. So this, what is going on here? This is the change in y. I don't know what any of these numbers mean, but that's okay. Show limit for x equals 0. No, I don't want to see that. Okay, this is kind of giving me some information. So let's just read this real quick. It's short enough. The line in red, which is this right here, passing through 2 points, large blue and smaller cyan, on the graph of the function f in green is a secant line. Great. We knew that. That was already known to us. The large blue point is at the location x subscript 0, f of x subscript 0, which you can change by dragging the point. Whoa, here we go. Now we're talking. Oh, that's interesting. It's getting wicked. Okay. You can also change delta x by typing in a value or changing the length of the purple. Oh, that's also cool. Didn't know you can do that. As you let x approach 0, which is moving it closer and closer, the 2 points become close together. Oh, shoot. It actually lets you approach 0, which is fun. The closest I could get is 0.0164. Let's see how close we can get. 0.0. I wonder how far it'll let me go. Let's see. 0.000000000. Enter. Okay, didn't let me do it. Oh wait, it did let me do it actually. That's funny. However, if you set delta x equals 0, then the secant line is not defined and the slope is also not defined. However, if delta x is very small but not 0, the secant line becomes very close to the tangent line, which can be thought of as the limit of the secant line as x approaches 0, delta x. If you click the show limit for x checkbox, then when you enter delta x equals 0, the applet instead shows the limiting tangent line, the slope of the tangent line, denoted by derivative y. I don't know what dy dx is. I think that's derivatives, which I haven't learned yet, and I forgot from when I did learn them originally. Is the limit lim delta x approaches 0, delta y over delta x, and is also displayed. Where is that displayed at? This is delta y over delta x. I guess that is it. Where is this line they speak of? Oh, is it this one right here? Where is the tangent line at? Is it in my unit circle? I know that tangent does have a line. I don't know where it is on the unit circle though. Is this? Oh, there it is, right there. I forgot how tangent lines work though. What exactly am I, what exactly is it that I'm looking at when I'm looking at a tangent line? Is the tangent line where, let me see, let me take a ballpark guess and then I'll Google to see if I'm right. I know what tangent is. Tangent is simply cosine over sine, right? X over y? No. It's y over x. No, it's x over y. It's x over y. It's got to be x over y. All right? Am I crazy? Am I talking crazy right now? Did I forget what tangent was? That's not good. I can't be forgetting what tangent is. It's cosine over. It's got to be cosine over sine, right? Let's see. I can easily answer this question myself by just looking at the unit circle. Let's see, the tangent of 30 degrees. Why are we doing degrees? There we go. The tangent of pi over 6 should be. Oh no, I had it wrong. It's sine over cosine. Holy crap. Chat, you couldn't help me? No one in chat was like, oh my gosh, bro, no, that's not it. You're wrong. You guys failed me, bro. You guys failed me. You're supposed to watch my back, man. Supposed to make sure I'm not making gaffes like this. No. Tangent is sine over cosine. Okay, so in my head, the tangent line is the point at which the tangent line is the line that intersects the circle at a point, right? I think so. I would like to think so. I'm sure it is. Okay. I think we're done with this, so we could go back to the video. Here. Okay, let's go back to the video.
Need 2 points. Yeah, that'd be great. Okay, cool. Now we're ready. I'm excited. First, we'll step off into Texas land. Do you trust me? You shouldn't. Here's the goal to this problem. I want us to find the equation of the tangent line to this curve at a certain point. that one. 1, 1. Well, let's go over to 1, 1, and let's put a point there. So P is the point 1, 1. I'm going to walk you through how we're going to do this right now, okay? I'm going to walk you through how we're going to make up a tangent line using this idea. Are you ready for it? Over here on this idea, we had 2 points, right? P set in stone, you're not going to move P. What other point do we have? Q. We're going to make a point Q. Q. What's the coordinates for point Q? Why don't you tell me? What's coordinates for point Q?
2.
We can't use actual numbers, right? That would be very good. So I know 2, 4 would be on there, and 3, 9 would be on there, 4, 16, and so on. But I want you to use actual points. In general, what are the points for, or what are the coordinates for any point? X, Y. Very good. Okay, X, Y. So now write down X, Y, and have your eraser handy. Have your eraser handy because I'm not going to have X, Y. I want to keep this in terms of one variable. Now, using your knowledge of what the function is, what's the function? Y equals what? Wait, say it again. Y equals what? Y equals...
What?
So instead of having X comma Y, would it be okay with you if I had X comma X squared? Yep. Yes, no? Because Y is X squared, right? So that won't matter. So erase that, and I want you to put X squared. Cool. All right. Now we have this secant line going from P to Q. P is a fixed point 1, 1. Q is a movable point X comma X squared. Would you agree that any point on this line will have the coordinates X comma X squared? No matter what I plug in, right? So that movable point, that's going to have the same coordinates all the way down. Now we have this secant.
Nah, man. Nah, man, no way. No way, bro. I refuse to believe anything this man is saying. Okay. I refuse to believe anything this man is saying. Oh, shoot. It's Black History Month. How am I just now realizing it's Black motherfucking History Month, bro? How can I forget such a thing? Nah, that's crazy. That's crazy, dog. Right, I'm gonna have to re-watch this because I'm not paying attention, but I'm also doing something that's important.
Here's what we want to know. We know that the equation for a line is y minus y1 equals m x minus x1, true? What we're trying to find is the equation for a tangent line. Here's what the equation for a tangent line would be. Pay close attention. It would be y minus y1, that's the same, equals the slope, but a specific slope. It would be the slope of the tangent line, true? Whatever the tangent line slope happens to be. So the slope of the tangent line, and then x minus x1. Now, the cool part about this, I'll recap this in just a bit. The cool part about this is we already have a point. What's my fixed point that I have? 1, 1. I already have 1, 1. So really what this comes down to is, can you find the slope of the tangent? That's why I said finding the slope of a curve at a point is the big deal for calculus. You already have the point. That's the easy part. The slope is the hard part. So we're going to try to find right now the slope of the tangent. Are you ready for it? Yeah. You sure? We're going to use the idea of slope of the secant. So we're going to take a break right now. We're going to come back to this. In case you're just a little bit lost, here's what we've done so far. This is y squared. I gave it to you. We fixed one point according to my problem. That's 1, 1. We've made up another point, a movable point, q. Q is at x comma x squared. Where did x squared come from? That's because it's y. All right, great. We now know that the equation of a line is this, so therefore the equation of a tangent line would be the same exact equation. It's just we'd have the slope of the tangent line. The problem is, it's very hard to find the slope of the tangent line without doing the limiting.
Nah, bro.
There's only one point there. So we're going to have to use the idea of a secant and make it into a tangent line by moving q really close to p. Do you get the idea? Basically doing that with this problem. So let's take a look at the slope of a secant. Our specific secant. Hey, by the way, do you remember the slope in general, the slope formula?
Yeah, I'm hella confused already. I'm not even gonna lie. Not even gonna cap. I'm mad confuzzled. Mad confuzzled, bro. Hella confused. I should not have kept playing the video, honestly. That was a mistake. Absolutely a mistake. I would say that was a gaffe on my part, actually. I'm just yapping for real, bro. What is up with this? Huh? Nah, this is crazy, bro. It's looking real sus. Okay. My hairline itches. I wish I knew why. Oh, I know why. I started wearing a do-rag to protect my hair when I sleep. And my hairline is growing in. I started wearing a do-rag to protect my sleep. If you don't know what a do-rag is, it's just like a little cap. If you've ever heard of a do-rag, it's probably from like rappers, or if you've never heard of it, then you probably know it from like rappers and stuff. They wear them, cover their hair. Gangsters, some might say. All right, let's rewind this.
True. What we're trying to find is the equation.
I literally actually stopped paying attention once he went over here, if I'm being honest. So sorry if you have to hear this over again.
Really close to, but never actually getting there. Again, why can't we get there? Need 2 points. Yeah, that'd be great. Okay, cool. Now we're ready. I'm excited. First little step off into Calculus land. Do you trust me? You shouldn't.
Do I need to write this example down, boys? I don't know.
Here's the goal to this problem. I want us to find the equation of the tangent line to this curve at a certain point. Specifically that one. 1, 1. Well, let's go over to 1, 1, and let's put a point there. So P is the point 1, 1. I'm going to walk you through how we're going to do this right now, okay? I'm going to walk you through how we're going to make a tangent line using this idea. Are you ready for it? Over here on this idea, we had 2 points, right? P set, so you're not going to move P. What other point do we have? We're gonna
Q.
Q. What's the coordinates for point Q? Why don't you tell me? What's coordinates for point Q?
I don't know.
We can't use actual numbers, right? That would be very good. So I know 2, 4 would be on there, and 3, 9 would be on there, 4, 16, and so on.
X, Y?
Actual points. In general, what are the points for, what are the coordinates for any point?
X, Y.
Very good. Okay, X, Y. So now write down X, Y, and have your eraser handy. Have your eraser handy because I'm not going to have X, Y. I want to keep this in terms of one variable. Now, using your knowledge of what the function is, what's the function? Y equals what?
X squared.
Y equals what? Y equals? So
X squared.
X, comma, Y. Would it be okay with you if I had X, comma, X squared? Yes, no? Because Y is X squared, right? So that won't matter. So erase that, and I want you to put X squared. Cool. All right. Now we have this secant line going from P to Q. P is a fixed point 1, 1, Q.
I guess everything he writes on the board I'm supposed to write, man. I don't study. I don't study. And I think that's why this math stuff has been so difficult for me. Because I never learned to study. I never studied. So trying to study makes it really difficult to study. But I'm going to do my best here. So I'm assuming that he wants me to write this. It's an example. And let's throw some examples on the board, shall we? Bam, create that line right there. Bam, create that line right there. Ooh, yes, sir. Give me a slope right there. Throw that line on there, letting me know that y equals x squared. We got this point. My phone's buzzing. It's nothing important, just Instagram. Nothing important ever comes from Instagram. So we have the point Q right here. This is x, and then we have f of x. Ooh, nice. But for this, I'm guessing using x squared. Then we have the point here, which is P. You guys can't see it, but his hand is in the way.
Q is a movable point x, comma, x squared.
I think that might be 1, 1. So let's erase that. This is the point P at the coordinates 1, 1. Wow, okay, let's go.
Squared. Would you agree that any point on this line will have the coordinates x, comma, x squared? No matter what I plug in, right? So that movable point, that's going to have the same coordinates all the way down. Now we have this secant line. here's what we want to know. We know that the equation for a line is y minus y1 equals m x minus x1, true? What we're trying to find is the equation for a tangent line. Here's what the equation for a tangent line would be. Pay close attention. It would be y minus y1, that's the same, equals the slope, but a specific slope. It would be the slope of the tangent line, true? Whatever the tangent line slope happens to be. So the slope of the tangent line, and then x minus x1. Now, the cool part about this, I'll recap this.
What?
The cool part about this is we already have a point. What's my fixed point that I have? I already have 1, 1. So really what this comes down to is, can you find the slope of the tangent? That's why I said finding the slope of a curve at a point is the big deal for calculus. You already have the point. That's the easy part. The slope is the hard part. So we're going to try to find right now the slope of the tangent. Are you ready for it?
Okay. No.
We're going to use that
No.
secant. So we're going to take a break right now. We're going to come back to this. In case you're just a little bit lost, here's what we've done so far. This is y squared I gave it to you. We fixed one point according to my problem, that's 1, 1. We've made up another point, a movable point, q. Q is that x comma x squared. Where did x squared come from? That's because it's y. All right, great. We now know that the equation of a line is this, so therefore the equation of a tangent line would be the same exact equation. It's just we have the slope of the tangent line. The problem is, it's very hard to find the slope of the tangent line without doing the limiting idea. You can't do it because there's only one point there. So we're going to have to use the idea of a secant and make it into a tangent line by moving q really close to p. Do you get the idea? Basically doing that with this problem. So let's take a look at the slope of a secant. Our specific secant. Hey, by the way, do you remember the slope in general, the slope formula? Slope is what over what?
y2 minus y1 over x2 minus x1.
Delta y over delta x. Specifically, in terms of our coordinates, what is our slope? That's what I'm looking for. y2 minus y1, yeah, over x2 minus x1, otherwise you get the negatives of that slope. So y2 minus y1, x2 minus x1. Do you follow?
Yes.
You feel okay with it so far? Just slope formula. What we're going to do, we're now going to find the slope of our secant. We've got the secant on the board, right? The secant will be the slope. I'm sorry, the slope of the secant will be the slope from points P to Q. Agreed? Let's plug in these coordinates. What do we have on the board? Plug in these coordinates into that formula. In our case, our y2 is what?
X squared subscript 2. 1.
Would be 1. What's our x2?
X.
x1. Okay.
1.
y2 minus y1 over x2 minus x1. Not sure if you're okay with that. So what we have so far secant is y2 minus over
X squared minus 1
x1
over x2 minus 1. Okay, all right. Okay.
Are you okay with it so far? Find out where the slope comes from. There's a couple notes I want to make at this point. First, I'm reiterating a lot of stuff here. I know that I am. I'm doing it on purpose because these are the key points of calculus. All right, you need to understand what we're doing. I would hate for you to do this class, right, and at the end of it, know how to take derivatives and integrals and have no idea what you're doing. You can be successful on just doing derivatives and integrals in this classroom. But if you don't understand what it is you're actually doing with those things, you don't even know what they are right now. But if you don't understand what you're doing, it's irrelevant. You're just now just doing formulas. It sucks. If you know what it comes from, what you're actually doing, I'm going to make sure you know, by the way, it's a little bit more interesting and you can apply it to more things. You get the picture? So right here, what we're doing, step number 1, is if we move Q close to P, this is going to become this. Do you agree? As Q, I'm going to use a new symbol here, approaches P. That means as Q gets really close to P without touching, the slope of the secant line approaches the slope of the tangent line. Would you agree with that statement? That's over here right now.
As Q approaches P, the slope of the secant line approaches the slope of the tangent. I can.
That's what this says right now, okay? As Q
I can
gets
rock with that.
The secant gets close to the tangent. How close? It depends on how close we get these things. If we get them so close it doesn't matter, then these become so close it doesn't matter. Agree? It's kind of neat, right?
I can rock with that.
Now, the problem is, here's note number 1. Here's note number 2. This is interesting, right? Where are we trying to find the slope? What point? 1, 1. Well, and what's the x coordinate for 1, 1? To find the slope of anywhere, you plug in that value, right? This gives you the slope of the secant line, true? Plug in 1. Plug in 1.
0 over 0.
No, you don't get 0. You get
Undefined.
0 over 0 is not 0. That's a big problem. 0 over 0 is undefined, right? Isn't that an issue? This is why, folks, this is the reason why you cannot have the point getting, listen, you can't get Q close to P because if you plug in 1, it's undefined. That means that you have the same point. So you can't let x equals 1, that's big time. That means double important. You can't let x equal 1. This is why we can't let Q equal P, because we only have 1 point, right? You can't find the slope, it fails, it's undefined at that point.
This is why Q cannot equal P.
If it does, if you try to find the slope of the secant at that point, move Q all the way down and plug in the x coordinate. If it's the same thing, you're going to get something that's undefined because you're trying to find a difference between points that don't exist, a difference that doesn't exist. And that's going to be you're divided by 0. But if there's no difference in the x-axis, that would mean you're divided by 0, you get something that's undefined, you get an undefined slope, that's a bad thing. So we can't let Q get all the way to P. True? All right. What can we do? Now this is going to blow your mind. You ready to get your mind blown? Like a mind grenade. You ever seen Yes Man? Watch Yes Man, it's so fun. Had a ripple. You had a ripple? It's called ripple. Right. If you've not seen it, that just sounded really stupid. You watch Yes Man, it's pretty funny. Now, so,
Bro,
next part.
that was a white people joke. For sure.
Blow your mind. Can you factor that? In fact, when
Yes.
and stuff like that, you know that if you have 0 over 0, it's factorable because of some stuff in mathematics that I haven't bored you with yet. But if you ever have some number that makes 0, it means that that's a factor. If you have some number, the same number that makes 2 polynomials 0, it means they have a common factor. We've got a common factor here. In fact, if you were to factor this is going to give you x plus 1, x minus 1, over x minus 1. Agreed? Okay. Do you see anything that simplifies out of that?
X minus 1.
Now, this is interesting, very interesting. What we're going to do is we're going to be able to simplify out this thing. Now, I know what you're thinking. Well, wait a second. Can't you not simplify out a domain issue? Isn't that a problem for you? And the answer is yes and no. It would be a problem normally. However, watch carefully. Are we actually letting x equal 1? Is q actually getting to the point p? No. So is x actually equaling 1? No.
No.
We're getting really, really close. I'm talking like 1.00000 forever and then a little bitty 1 at the very end of it. Really close. But it's never actually equaling 1. So keep in mind, when we do this, we're not getting rid of any we're not really altering the domain whatsoever because we already knew x wasn't equal 1. So we have this little restraint already, x isn't going to equal 1. So then what we know is, okay, the slope of the secant now equals x plus 1. Were there any questions on this? Because I got to erase it. Do you have anything? All right. Is this making sense to you? Do you see where
Sure.
it came from? Do you see how we can factor and simplify it? And now we get down to here. We don't have any problems not eliminating the domain issue because we're actually not letting x get equal to 1. It's just getting really close to it. Here's the jump that we're going to make, okay?
I just hand waved a little bit, but it's okay. We'll let it slide for now.
Here's the jump. So that was true. That's what we have down. What I'm asking
Okay.
you is, as q gets closer to p, so basically as x gets closer to 1, what happens?
What happens is x gets closer to 1. That's a good question.
Q gets closer to p, that means the x variable is getting closer to 1. As x gets closer to 1, can you tell me what happens to the value of the secant? Let's try some, okay? Think about this for a second. Just do a little bit of math with me. Let's say we started at the point 4.
Okay, let's try to do this by myself. So he says, what happens to the secant line as x approaches 1? Well, we know that secant can't equal 1, or we know that x can't equal 1 because when x is 1, secant is undefined. So, and we just did this with the applet, but I want to do it in my head. X can't be 1, but it can approach 1 from 0. So 0 plus 1 is 1. The secant line is straight. Straight for every y, 1, x 1, you get a straight line. Oh, well, we know this. And as it gets smaller and smaller, right? Or no, actually, I think you should go towards 0 from 1. All right, that's what we already determined, is that x is approaching 0. X is approaching 1 from 0. Right? Actually, let me see.
16, so x would now be 4. Plug in 4 here, how much would you get? Okay,
5.
Let's move it down to 3. Plug in 3 here, what would you get? Move it down to 2, how much would you get? Okay, move it down to 1.5, how much would you get? 2.5. Move it down to 1.3, what would you get? Move it down to 1.1, what would you get? Move it down to 1.01, what would you get? 2.01, good. Move it down to 1.00001, what would you get? Move it down to 1.00000 forever, and then a little 1 at the end, what would you get? 2.0 forever and a little 1, would you? Would you say that as this thing gets closer to 1, the slope of our secant gets closer to 2?
Yes.
Because I'm plugging things really close to 1, I'm going to get out things that are plus 1, really close to 2. Does that make sense to you? Our secants will be really close to 2. Here's what that says. This lets us make the jump. This is a limiting position. It says that we know the limit of the slope of the secant line is 2. What that means for us is that the slope of the tangent line actually is 2. That's the jump.
What?
It says the secant line at this point, if x gets super, super close, really, really close. If x gets really, really close to 1, the secant line gets really, really close to 2.
No, that's crazy, bro.
But I can make the jump that if I could let x equal 1, the slope would be 2. That's the jump there. Do you guys see the jump? This is the using limits to make the jump between a secant and a tangent. So because the secant's approaching 2, we say, okay, we got this. That's called a limit. We're going to talk more about limits later on. But the jump is going from here to here. Now can you fill out this equation using that information? Sure. We know that it would be y minus y1, which is 1, equals the slope of the tangent. Hey, we know it's 2x minus 1. Now, of course, we don't generally leave things in point slope. We'll solve them. Do you see where the 1, and the 2 are coming from, folks? Our point is 1, 1. Our slope is now 2. That's the slope of the tangent. If we solve it, we get y minus 1 equals 2x minus 2. Add the 1, y equals 2x minus 1. That's the slope of a curve at a freaking point. That's awesome. Oh my gosh, isn't that cool? We just found the first tangent line to a curve that you've done. Now, granted, it's not a very hard curve.
Okay, so we're going to extrapolate y minus y1 here. So this all moves towards this, which says that y, which we don't know because we're looking for it, trying to find the slope. Y minus y1, which is 1, equals, well, m tangent, we already know, as we found here, is 2 times x minus, what we know, 1. We can say y minus 1 equals 2x minus 2. Add the 1, we could say y equals 2x minus 1. Crazy.
Curve, but here's what it is. I'll show it to you. You can actually graph it. Here's minus 1 crosses there. You go up 2, 1, 2, over 1. Oh, that's the point. And if I graph it, it intersects at only one spot. That's it. That's a tangent line. Isn't that awesome? Your mind should be blown. Is that why you're looking at me stunned? Like, yeah. Is that your stunned face? It should be your stunned face. Okay. Now, by show of hands, after 40 minutes of doing one example, how many people want to show we talked about? Good. Do you have down right now the basic idea for calculus? This is a basic idea. Using limits to find this tangent of a curve at a point. Is it going to get more advanced than this? Yes, of course it is. But that's the basic idea. And we're going to do things differently when we actually get to the calculus. We need to study limits more first, but we will get there. Now, the next thing we got to talk about is the different problem. I'm not going to spend a whole lot of time on it. I'm basically just going to introduce it to you because I know for sure you guys are not going to remember this by the time we actually get to area under a curve. So I'm going to introduce it to you again. But for right now, I want you to just get the idea about what's going to happen later on. Okay. So the area problem.
And then we get the area problem, huh? Okay.
Here's the area problem. Area problem says, can you find the area under a curve between 2 points? The answer is yes, you can with calculus. Only, how are we supposed to do this thing and let limits work for us? Here's the plan. Firstly, can you find the area the way it is right now? No, it's got a curve to it. You can't find areas with curves in them. So what maybe would be an idea?
You can approximate it by making it like a rectangle.
Oh, I could, yeah, sure. If I did this and said, okay, from here, I just want to make a rectangle. Would that be an approximation? Mm-hmm. Would it be a good approximation? No, not really. However, what if I did, okay, I don't want just one rectangle. Maybe I do this. I say, okay, I want a rectangle from here to here, then a rectangle from here to here, then one from here to here, then one from here to here. Is that a better approximation? The missing area is smaller, yes? That's the idea behind the area problem. What we're going to be doing is making rectangles. Why rectangles? Well, let me ask you, can you find the area of a rectangle? That's why rectangles.
Yes.
And they're easy to draw. So if we make lots and lots and lots of little, teeny bitty, weeny little rectangles like that, all the same width, but going the entire length of our curve, and we add up all those rectangles, are we going to have a pretty good approximation of the area? And in fact, if we make those rectangles infinitesimally small, so whereas you couldn't even slip a piece of paper between them and then add them up, is that going to be even better? In fact, if we stuck an infinite number of rectangles between this point and this point, which you can do with limits, we're going to have a perfect area, and that's the idea for the area problem. You stick an infinite number of rectangles in there and add them up. It's going to involve limits because we're letting some number go to infinity. You can't ever reach infinity, but a limit will take care of that for you. That's the idea behind the area problem. Does that make sense?
What?
Kind of the idea of the rectangles? Trust me, we'll get much more involved later. You have no idea how to do this right now. Don't worry about it, okay? We're not even going to do a problem. We'll do that later, chapter 4 or something like that. So, let's define a limit. What a limit says in English is, what does the function do as a variable approaches a given value? That's what it says in English. So, limits. What does the function do?
Erase. Why is it not erasing?
As the variable approaches a given value.
Okay, so limit says, what does the function do?
That's the question. Now, do we care what happens to the function at that value? The answer is no. The limit isn't about getting to the actual point. It's about what happens as you're approaching that point, getting really, really close. You see the difference there. In the previous example, we couldn't actually get to 1. Do you remember why? Some of you are zoning. You're zoning out. You can't have 1 point on the line. We'd also make a undefined point, right? If we undefined, that would be bad. But we saw what happens when we get really close. The function got really close to something else. That's the idea of a limit. So we don't care what happens as you get to the value. What happens as you approach the value? For us, this is exactly what we did actually, kind of in our heads. What happens? What happens to x squared as x approaches? Let's do 2. That's x approaches 2. I could have written in English, but that's just as valid. What happens as x approaches 2? Now, do we care what happens if you plug in 2? No, don't care. What I care about is what's going to happen if I draw this table right here with x and f of x. And I say, I'm trying to get to 2. I don't care what that value is. What I'm trying to see is what the function is doing as I'm getting close to that thing. So what's happening as we approach it from the right? What's happening as we approach it from the left? Give me some, oh, yeah, I already ruined it. Give me some numbers to the right of 2. Some numbers to the right. 3. Give me something smaller than 3. Like 2.5 is that's what I was about to write. So I just ruined it. Give me something a little bit closer to 2. Closer than that, maybe. 2.1, yeah, or 2.01. We want really close, right? So 2.1, and then maybe 2.001. That's pretty close. Take your calculator out the way. Now let's go the other way. Give me a number that's smaller than 2 that we want to work our way up from this way. Okay, sure. How about we keep it kind of symmetrical? 1.5, I like that one. We'll do 9, right, and 1.5.
No, I dropped my.
How about that? Does that work for you? Take those numbers, our function's x squared. Let's look what happens to the function as we plug those things in.
Okay, so we have. I like to use blue for examples. Really pops. Really makes me feel good. And so he's asking, oh no, something. What the heck is that? Oh, some solder got stuck to my Apple Pen. Uh-oh, it's not coming off either. Oh, there it goes. It's lead solder, so hopefully no one ever eats it. That would be pretty bad. Especially my kitten. That would be so bad if my kitten that hates me ate the lead solder. I wouldn't even want to know what would happen. I'm just kidding. I love her even though she hates me. What happens as x approaches 2? Good question, Professor Leonard. So we're going to create ourselves a table. Boom, bam, bada bing, bam, pow. Okay? And we're going to have 1.5. Wow, what is that? What the heck is even that? Okay, 1.5, bam. What does that say? Oh, 1.1. 1.1 it, and then 1.001 it. Boom. Then we have 2, which we can't use because that is where we're trying to get to. We have 2.1. Wait, 2.01. Let's get these numbers in order, Nick. 2.001. Okay, 2.1. And finally, we have 2.5, I would imagine, yeah? Cool. Now we're caught up with Dr. Leonard. Notes. Gotta take notes.
If you plug in 2.5, what do you get when you plug in 6.25 or something like that? Plug in 2.5. Do you get 6.25? Yeah. Okay. So we'd start with 6.25. What we care about is, does this side, look at the board, if we go this way and we go this way, do they meet up at the same point? That's what we're talking about for limits. Now this is a very easy example. We're working with x squared. We know the answer is going to be 4, right? It should be 4. We're going to see if that actually happens when we evaluate our limits. Plug in 2.1, someone out there. Tell me what you get when you plug in 2.1, would you? 4.41? Okay, that's close to 4. Tell me what you get when you plug in 2.0.
This is a reminder. Feed Luna.
1. 2.000.
This is a reminder. Feed Luna.
Wait, what's it? 4.004.001. How about that? Like that? How about 1.5? Oh, that's 225, isn't it? How about 1.9? Plug in 1.9. What do you get when you do that? X squared. 3 point. And now do 1.999. 1.999. What do you get? How much?
3.960.
3.960?
Come on. Come on.
Yeah. Okay, cool. What's going on here? Let's see. With a limit, we really don't care about what happens at 2. Because a lot of times what you're going to find out is that we deal with limits where you can't get to that number because for some reason it's undefined, like our slope problem we just had, okay? So we're trying to figure out what's happening from the right and from the left and seeing if those are heading towards the same exact value. Are they? We're going from 6 down to 4, down to 4.04. Where's this heading? Towards 4. Where's this heading? It's heading towards 4. What we would say right now, this is how you write it. A couple notes about this. The function must approach the same value from both the left and the right. So this is from the right, this is from the left. The function must approach the same value from the left and the right for the limit to exist. If it does, here's how you write the limit. What you do is you put a little lim undercase, which kills me because I can only write in capitals. So you put the limit, you put the variable you're working with, you put that little arrow which I already told you is approaching, and you put the value to which x is approaching. X is this one. Where are we trying to get to on our x? So we're trying to find out what happens around the point x equals 2. Does that make sense to you? So you say the limit as x approaches 2 of your function. What was our function? Say it again. X squared. The limit as x approaches 2 of our function is equal to. What did the function approach? Here's what this says in English, okay?
Dang.
Does the function approach as the
Bro, I was in the zone, dude, and Marvin just scared the crap out of me, dude. Why did he jump on me like that? Marvin, you gotta get down, dog. I can't do this with you writing. I love you so much, buddy. I really do. Bro, I've been giving you love all day, man. This ain't nothing for you. You would die if you drank this. I was in the zone. And Marvin scared me. All right, Marvin. Gotta get down, buddy. See you later. Love you. Bye. I was drinking this Coke. I was lost in a trance and my stomach was hurting. Marvin broke me out of it. I feel like I was quiet for a really long time there. But I was just trying to... It gets hard not to get quiet, honestly. It gets hard not to get quiet. What can I say? What can I say? There's not much to say. Okay. The function must approach the same number. Oh, that's what I needed. From the left and the right for the limit to exist. For the limit to exist. That's ugly. Let's get a better one. Okay. And then he writes down limit. So let's see how that looks.
If it does, here's how you write the limit. What you do is you put a little lim undercase, which kills me because I can only write in capitals. So you put the limit, you put the variable you're working with, you put that little arrow which I already told you is approaching, and you put...
Okay, so you write, this is important, so I'm writing in red. Put lim. Put the variable you're working with. Approaches 0.
And you put the value to which x is approaching. X is this one. Where are we trying to get to on our x?
Oh.
So we're trying to find
2.
out what happens around the point x equals 2. Does that make sense to you? So you say the limit as x approaches 2 of your function.
The limit as x approaches 2.
X squared. The limit as x approaches 2 of our function is equal to. What did the function approach? Here's what this says in English, okay? Look at the board. What does the function approach as the value x approaches 2? What's the function approach as x approaches 2? What's it going to do? That's the limit.
4.
In general, we have this.
Okay.
This will be the last bit. We have a limit of a function is equal to some number. That's what capital L is. That would stand for the limit of this function as x approaches a. It's what the function's tending to do from both sides as x approaches one single value. The only thing that we need to know is the limit really doesn't depend on getting to a. Right? X is never going to equal a. X never gets a. We just care about what's happening to the value of the function as x is getting really close to a from both sides. Up here on the board, what's happening to the function as x is getting really, really close to a from both sides. It's getting really, really close to 4. That's the idea of limit. How many people understand the idea of a limit? Cool. Next time we'll work on how to find some limits.
I understand.
All right. So if you remember from last
Oh, whoa, he's got a button down. A little too big for him. A little too big. When was this? When was this recorded? 12 years ago? 12 years ago. Nah, bro, this isn't the 2000s, Dr. Leonard. I mean, it is 2000s, but like early 2000s, bro. You can't be out here wearing big shirts. I am cold. I am cold. Okay. The interesting thing about like self-teaching, right? The interesting thing about like learning things without the help of anyone else, right? I mean, obviously he's helping me, but I think you guys know what I mean. You kind of just go. And you go and you go and you go. Like here, normally, for most classes, you would go to this class, take a few homework, do some homework, and then you just go home. But this is like, now you sit through the whole hour, 27 minutes. But it seems like these classes are only like 30 minutes. Oh, I guess the class is about an hour. I wonder if we gave them homework. Let's see if I could do any of this homework that they have at the bottom of this. For the following exercises, points P, 1, 2, and Q, X, Y are on the graph of the function f of x equals x squared plus 1. Complete the following table with the appropriate values: y coordinate of Q, the point Q, X, Y, and the slope of the secant line passing through points P and Q. Write your answer to 8 significant digits. So I need to find, whoa, A, B, C, D, E, F, G, H, I, J, K, L, M, N. Okay. Yeah, what? Maybe we haven't gone over this, because, yeah, I don't understand what this means. Honestly, I don't, genuinely, no clue. Big lost. My stomach is doing twists and turns. I haven't had any food today. All I've had was Zins, vapes, and what do you call it? Zins, vapes, and God knows what else, actually. Okay, so I don't think I'm quite ready to be doing this yet. Hopefully after his next class, I will be able to do it. So let's see here. Give me a sec, guys. My school, I was like getting financial aid for my school, and I never got financial aid before, and obviously there's all this stuff going on with the government, so I'm just trying to make sure that it's going through. They sent me a couple emails and stuff, so I'm just checking those real quick. My financial hold was released. What does that mean? I'm a bit confused. Sure. I mean, if we say so. I don't really know what they're talking about, but absolutely, I agree. I'm talking about these. You guys can't see it, obviously, because you can't look at my finances and whatnot, but what are they talking about? I had a financial hold on my account, right? I had a financial hold on my account. And then I'm like, okay, all right. Reach out to them. They say, oh, the money is like, you're good. The money's good. And then now they're saying that my financial aid was rewarded. Oh, this is the disbursement date. I'm so confused. So my disbursement date is in a few days. Nice. There you go. Yeah, I'm a bit confuzzled. $436. Okay. So They're only giving me, oh, this is so confusing. They're only giving me 3,000 for this term. But then they're saying, what? How do I pay my loan in the first place? Like, there's just no information on any of this, dude. It's so annoying, bro. It's so annoying. This is why I never wanted to do like any of this, because I just don't, I don't get it. I don't understand it. It's like not made easy to be able to understand. I feel like that's why so like people find it predatory. Like they're charging me, what was it, 8%? They're charging me 8% on this loan, dude. This loan that's not going to help me. Like, holy, bro, are you being serious right now? Loan repayment planning. Like, what are we even talking about right now? I don't even know how to see like where my money is coming from. I don't know who has it. I don't understand this. Like, who is my money coming from? I don't get it. Let's see. Sorry guys for the delay here. I'm just trying to figure this out. What the heck is the student clearinghouse? I feel like I signed up for student clearinghouse for a reason, and I don't really remember why. Oops. Why do I have 32? What? Okay, so my program tuition. Okay, let's see. My program tuition was $4,085. I personally paid that. Okay. All right. Make a payment. The current balance is this. The charges are that. Estimated aid is that. So what are we talking about here? Like, what does this have to do with me? I'm so confused. I'm so confused. Whatever. I don't know what they're talking about. I guess I'll just have to wait to see what happens with this because I'm lost. I'm lost and I'm big hungry. Big Stangalaka. What do I have for dinner today? Or lunch? Low-fat cottage cheese and breakfast links. Nice. Nice. All right. Let's finish this video. We have about 40 more minutes left on this video. Let's just, we're grinding. Oh, I gotta feed the cats. I can't wait 40 minutes to feed the cats. Okay, well, I'm gonna go feed the cats really quickly, and then I am also going to make my lunch. Shouldn't take too long. Yo, I have to handle some in real life stuff. So, oh, no one's here. So, adios. Sadly, gotta go handle some stuff. So, peace.